Hello everyone and welcome to Signals, Systems and Signal Processing with Wolfram U. In this lesson, we will discuss Laplace transform. This lesson introduces the Laplace transform, which plays an important role in the analysis and design of LTI systems. Laplace transform is a generalization of the continuous time Fourier transform. Laplace transform is useful in transforming the differential equations into algebraic equations, in reducing electrical networks to simultaneous algebraic equations. It also easily incorporates the initial conditions and impulsive signals. The Laplace transform, also known as the bilateral or two-sided Laplace transform, is defined as shown here. Here, S is a complex variable. As we just mentioned, the Laplace transform is a generalization of the continuous time Fourier transform. Letting S equal to j omega, the Laplace transform integral reduces to the continuous time Fourier transform of the signal x of t. So in the general case, letting S equal to sigma plus j omega, the real part and the imaginary part, the Laplace integral becomes the expression shown here, which can be interpreted as the continuous time Fourier transform of the modified signal x of t times e to the power minus sigma t. So using the condition for existence of continuous time Fourier transform, the Laplace transform converges if x of t times e to the power minus sigma t is absolutely integrable, as shown here. This means that the Laplace transform exists for all functions x of t that do not diverge faster than an exponential function. Also, the range of values of sigma for which the Laplace integral converges is what we call the range of convergence of the transform. As an example, let's find the Laplace transform of the unit step function. Using the function bilateral Laplace transform in the Wolfram language, we find the Laplace transform and the condition under which this result is valid. Basically, the region of convergence for the Laplace transform. Finding the Laplace transform by hand, we use the formula for the Laplace transform, replacing x of t with ut, or with 1, taking the integral from 0 to infinity, and evaluating the integral gives us the expression shown here with the limit of e to the power minus st, where t goes to infinity. Note that the complex value s equals sigma plus j omega, and so e to the power minus st can be simplified as shown here. And therefore, the limit is equal to 0 when sigma, or the real part of s, is positive, and it goes to infinity when sigma, or the real part of s, is negative. With this, the Laplace transform of x of t is equal to 1 over s for real parts of s that are positive. We can present the Laplace transform pair with the region of convergence as shown here. For the example that we just had, the Laplace transform of the unit step was found as shown here. Since s is a complex variable, we can write it as sigma plus j omega and rewrite x of s, the Laplace transform, in terms of sigma and omega. The magnitude of the Laplace transform, therefore, will be 1 over absolute value of s, which is equal to the expression shown here. And the phase is the angle of the complex term, which can be simplified further and expressed in terms of arctan. If we plot the magnitude of the Laplace transform, we can see how it changes in terms of omega and sigma. For our second example, let's find the Laplace transform and its region of convergence for the signal x of t defined as the exponential function shown here. Using the Wolfram language, we can simply use the function bilateral Laplace transform to find the Laplace transform and the region of convergence. We can also plot the magnitude of the transform and the region of convergence for a equal to 1. We get the Laplace transform pair and the region of convergence as presented here. Now let's look at another signal that is slightly different. It's anti-causal, and let's find the Laplace transform of this new signal and see how it is different from the previous example. Using the Wolfram language, we find the Laplace transform as shown here. If you compare the value of the Laplace transform for the left-sided exponential to the previous example, you can see that the Laplace transform is equal for both signals, but they have different region of convergence. As we did for the previous example, let's plot the magnitude of the Laplace transform and the region of convergence. With this example, you can see that both the Laplace transform function and its region of convergence are necessary to uniquely associate a signal with its Laplace transform. Finite duration signals that are absolutely integrable have an ROC that covers the entire S-plane. ROCs are always either vertical half-planes or strips bounded by the roots of the denominator of the Laplace transform. Half-planes for the left-sided or right-sided signals and vertical strips for two-sided signals. For the two-sided signal shown here and its Laplace transform together with ROC, here you can see the plot of the signal, how it changes over time, and the ROC. You have a vertical strip bounded between the two zeros of the denominator of the Laplace transform, 1 and -2. Square integrable signals have Laplace transforms with ROCs that include the imaginary axis. Also, if the ROC does not include the imaginary axis, the corresponding time signal must be unbounded. Three bounded signals and their region of convergence are shown here. In all of these examples, the imaginary axis is included in the region of convergence. You have the left-sided signal, the two-sided, and the right-sided signal. As we mentioned before, the bilateral Laplace transform is a generalization of the continuous time Fourier transform. Starting with the Laplace transform integral, if we replace s with j omega, it will reduce the transform to the continuous time Fourier transform as shown here. As long as the imaginary axis lies in the region of convergence x of s, the Fourier transform can be obtained by evaluating x of s and replacing j omega for s. For example, given the Laplace transform shown here with the region of convergence being real parts of s greater than -1, the Fourier transform can be obtained as shown here. Here we are showing the magnitude of the Fourier transform in red superimposed on the magnitude of the Laplace transform. The Laplace transform of LTI systems takes the form of a rational function as an example that we had here in this lesson and also the second example shown here. The Laplace transform takes the form of a ratio of two polynomials whenever x of t is a linear combination of real or complex exponentials, or whenever modeling the LTI system results in linear constant coefficient differential equations. In the general case, the ratio of the two polynomials has the form shown here. We call x of s strictly proper rational if an is non-zero and the order of the numerator polynomial m is less than the order of the denominator polynomial n. And we have an improper rational function when m is greater than or equal to n. In this case, we can always rewrite the rational function as a sum of a polynomial and a proper rational function. xp of s denotes a proper rational function here. Also, we call the roots of the numerator polynomial zeros and the roots of the denominator polynomials poles, and we can always express a proper rational Laplace transform explicitly in terms of the poles and zeros using a factored form as shown here. And the constant value k is called the scale factor. Here we have a rational Laplace transform, and we can find its zeros. the roots of the numerator of x of s, and the poles, the roots of the denominator. A common visualization of the Laplace transform is simply a plot of the location of these poles and zeros. The poles are shown in blue and the zeros are shown in orange. And as before, we can have a surface plot of the magnitude of the Laplace transform as shown here. In this lesson, the Laplace transform was introduced, an integral transform, very important in the study of continuous time signals and LTI systems. We went over the definition, the condition for existence, the uniqueness. Basically, we saw that we need to always represent the Laplace transform together with its region of convergence to uniquely describe a signal. We discussed several examples evaluating the Laplace transform, and we went over useful graphical representations associated with the Laplace transform, such as the ROC, poles and zeros, and plots of the magnitude of the Laplace transform.